Yeah, thanks a lot for the opportunity to present our research. It's an honor, and I'm very pleased that we are allowed to visit you here in Taiwan, where the global chip manufacturer is located. I was very eager. We were very curious to see Taiwan, and we are very happy to be here. Yeah, so for like more than 20 years, we are involved in development of electronics for high-energy physics experiments at the research institute called CERN. CERN is located at the border between Switzerland and France. There's the Large Hadron Collider, which you see here, which is the world's biggest particle accelerator. So they accelerate protons to very high energies and bring them to collision. And then physicists study their particles which are generated after the collision and how they interact. And maybe you know the famous Higgs boson, a special particle which has been discovered there in 2012. So there are several experiments to measure the particles and their properties. One of them is the ATLAS experiment, where we are members, we are collaborators. It's a huge device built of several sub-detectors, which are like onion-shaped. Each one has a special function, like to measure the energy, the tracking, and the momentum of the particles. And we are involved in the very center of this experiment, which is the pixel detector, which you can see here. It has several layers. I have also a nice photo for you to see it. So here you see three layers. In future, it will have 5 layers. And each layer, the layer is shaped like a barrel. And each barrel is formed of several modules. And the module I've shown here in more detail. It consists of a sensor, which is shown in yellow. Unfortunately, I cannot point. Which one is for the? It does not work. Here it works now. So it's formed from a sensor, which is a pixelated PN junction, either planar shaped or with 3D geometry, so where you have the electrodes formed like small pipes going through the complete thickness of the detector. Then we have 4 chips to read out one sensor. So these chips are quite large, built in 65 nanometer technology TSMC, and they're close to the largest size which is recommended from TSMC. And then the sensor and the readout chips are flip chip bonded to the sensor. So the main structure of the chip is the pixel array, where the charge is collected of the particles which are hit, and the timestamp is generated. And then we have also some periphery, which is shown here as the largest part of the chip, while you can see here that the pixel array is the largest, while the periphery is quite small. And there we have some trigger logic, because not all data is read out, only interesting events are read out. And we have some biasing, a band gap. And the part of the chip where we are involved in this chip especially is the powering, which is located very close to the PET frame. So this chip was designed by a collaboration of 30 institutes around the world, and we were in charge of the powering. So here you can see a picture how the old version of the pixel detector has been installed in the ATLAS experiment, and next year we are planning to upgrade the detector and introduce the new chips which we have developed. So in this environment, we have very special challenges. One is the very high radiation. So we face, over a lifetime of 10 years, 1 gigawatt of irradiation, which in gray it's 10 megagray. Just to relate, in a near-orbit space mission, in a satellite, for example, we have a total ionizing dose of 100 kilorad. 100 kilorad in comparison to 1 gigawatt is magnitudes of orders higher, so very, very high radiation. This radiation influences especially the oxides of transistors. So the radiation ionizes electron-hole pairs. The electrons can tunnel out of the oxide, while the holes stay in the oxide and, for example, change the threshold of the transistors or create additional leakage. So to solve this, we have to go to small oxides below 5 nanometers. So 65 nanometer technology is wonderful, very radiation hard. So we compared it with other vendors from, don't name them, but TSMC had the best radiation hardness. So that's why all the CERN development is done in TSMC. Unfortunately, even the newest technologies, they have a thick oxide around the transistor, the field oxide, right? And there we have, again, these charges trapped, but we have to avoid minimum size transistors, go to larger widths, larger lengths, and then the influence is rather small. So this is the way to design radiation-hard circuits. You have to go to core transistors only, no I/O transistors, no thick gate is allowed. And then you have to avoid minimum sized WL ratio. And then it's quite radiation hard. Another problem is the single event effect. So we have a very high hit rate of 1 gigahertz per square centimeter. So we measured that we have SEU rates like 100 hertz over the whole chip. So these single event effects, they create upsets in memory and in flip-flops. So 1 becomes 0 or 0 becomes 1. And also in the logic, which is then called single event transients. And if the clock is synchronized to the transient, it's also becoming a single event upset. So here we have to take into account these errors and introduce redundancy, protection, and correction. And one more problem we have in this experiment, we have a very strong magnetic field around the experiment, like 2 to 4 Tesla. This is to distinguish between charged and uncharged particles. The charged particles, they are influenced by the Lorentz force, and they bend, while the uncharged particles, they go straight ahead. And by this means, we can differentiate between charged and uncharged. Problem is here that we have problems with power management, because DC-DC converters, they use coils, and the coils have a ferromagnetic core, and the ferromagnetic core at 2 Tesla saturates and behaves like air coil. And to create inductances with sufficient, so coils with sufficient inductance, we would need very big volume air coils, which we have no space to use. So this is a major problem. It is considered that DC-DC circuits cannot be used in the experiment due to this fact. Yeah, and exactly this is the problem, that we have a low power efficiency. I did the math with the cable resistance, current consumption of the chips and the supply voltage, and if you do the math, you see that nowadays pixel detectors, as it is installed at the moment, has only 20% power efficiency, which is very bad. So most of the power is lost in the resistor of the cables due to IR drop. And since we cannot use DC-DC conversion, it is considered that it cannot be used. We had another idea. We connect the modules not in parallel, but in series. Why is that a good idea? Because if you connect the modules in parallel, and let's say each module consumes 1 amp, if you have 10 modules in parallel, you consume a total current of 10 amps, right? But if you put them in series, the current is flowing from one module to the other and stays the same. Independent of how many modules you connect in series, the current is always the same. Only the voltage which drops across the whole chain is increasing. So we have the current of only one module, which goes from one module to the other and to the other. It does not scale with the number of modules. And this increases the power efficiency to like almost 99%. And this is the way the ongoing upgrade will be installed. The problem here is that if you have a problem on one module in the chain, the complete chain is not powered anymore, and you have a large part of the experiment which is blind. You are not sensitive anymore, you cannot measure. And that is why we want to introduce as much as possible redundancies to be fail-safe. So we need here some, so we have a constant current source instead of a constant voltage source, and we need on the chips regulators which translate the constant current into a constant voltage. Yeah? And we want them to be operable in parallel on module level, so the whole chain is in series, but on module level we want to have them operating in parallel so that if one regulator breaks, the other can take over. Straightforward idea would be to use a shunt regulator. A shunt regulator regulates the current flow through the load. All the current the load does not need, it's shunted by a shunt transistor, and by this means the voltage across the load is regulated. Problem here is that these regulators have a very steep IV characteristic, and if you have offset, which introduces a variation in the output voltage, and you have several of these regulators connected in parallel, the one which generates the lowest voltage takes over the whole current and eventually breaks. Yeah? So you don't have an even distribution of the current across the several regulators, only one regulator is operating. So what we would need is an IV characteristic which has a lower slope, because then even if you have different voltage where the regulators kick in, there is some distribution across parallel connected regulators. And of course, this distribution becomes more homogeneous if the offset is kept as small as possible and if the slope is as low as possible. This is the goal. So one idea to how to solve this was designed 10 years ago during my PhD thesis, and now it's introduced into the experiment. It's a regulator which is called shunt LDO regulator. It's a combination of an LDO regulator, which you can see here. It's a standard LDO regulator, voltage regulator, and in addition a shunt regulator. It's two in one, right? So this guy here is taking voltage regulation, and this one is taking care of that the current flow is always constant. Now, I have not the time to go into details. We need also some more circuitry to define a reference current, and this reference current then takes care that the defined reference current is also flowing into the regulator. So if you do the calculation at the end, you see that the dependence between voltage and current at the input port of these regulators is described by this formula. And here you can influence the slope of the input voltage characteristic. And if we plot this function, you see now voltage and current, they are twisted on the axis, but you see that we have exactly what we need. So we have some offset voltage and then a slope, and we can configure by adapting one resistor value the slope of this curve. And we can choose it with respect to the system needs, such that the current distributes homogeneously as much as possible across the parallel connected regulators. So this works very good. It's installed at the moment. Next year it will be running at the LHC, at the ATLAS experiment. But we did not like the let's say, dogmatic approach. DC-DC conversion does not work in the experiment. So we were thinking, how should be a DC-DC converter be designed such that it can work with high radiation hardness and be operatable in this high magnetic field of 2 Tesla. Because if we would have then this possibility, we could make a scheme which power supply scheme, which is shown here. We have DC-DC converters integrated in our chips, and we can design a multi-stage approach. So have another DC-DC converter farther away from the pipe, where the radiation dose is smaller, and we can use some more conventional approaches. So problem is that we need a very high voltage conversion factor. So even factor 16 does not reach the sufficient power efficiency which we need. So very likely we have to go to 32, and we have to do that in several steps. And the farther away we are from the beam pipe, the less radiation dose these converters will consume. So what we focus first on is the DC-DC converter, which has to be integrated into the chip. And the idea which came up and which also is working properly, so Jeremias Kamkete, who's also here, designed the circuit, is to do the following thing. We use a cascoded power stage, cascoded thin gate oxide transistors, which are usually used only in the core side of the transistor, 4 PMOS, 4 NMOS. And by this means, we can handle the high supply voltage. This is 4 times higher than the nominal supply voltage of the core transistors, and be radiation hard, because these core transistors have a very thin oxide. So by this means we solved the radiation hardness issue. Problem is, you need a specific special driver stage which adapts the gate potential such that there's no time any over voltage. So because these transistors, for example, this technology, they can bear 1.2 volt, but we apply 4.8 volt, and then the gate potential has to switch accordingly, that there's no over voltage. But this works fine and very reliable. The other thing is that we cannot implement, we cannot use inductances with ferromagnetic material. And to realize a inductance with air coil only, we need very small values, so like 100 nanohenry or something, 20 nanohenry. And then for having a system which is working properly, we have to operate at very high switching frequency. The higher the switching frequency, the smaller you can choose the inductance of the DC-DC converter. And we targeted 100 megahertz. And to get an operable DC-DC converter, we had to solve many issues like crosstalk and kickback, which is a problem at high 100 megahertz switching. You know, when you have switching signals at 100 megahertz, 4 volts, 5 volts, this introduces a lot of crosstalk and kickback. So we have to optimize the control circuit such that it is possible to operate in this condition. And what we also saw is that we had a lot of ringing on the wire bonds. And this then disrupted the switching operation. And we could not reach a stable the operation like the pulse width modulation. It was, you know, randomly the pulse width became larger, smaller, larger, smaller because of the ringing on the supply lines. And to solve this, we tried two options which work very nicely. So either we use external bondable silicon capacitors, which are placed very close to this chip so that the wire bonds from the DC-DC converter to this capacitor is very small, and you get very small inductance, and by this means the ringing frequency is shifted to very high values. This is one option which works nicely, but creates a lot of mechanical complexity and may introduce reliability issues. And the other more convenient approach is to introduce the decoupling capacitors on chips, but then you have to spend a considerable amount of the chip area for the additional capacitance. But these two options are around, and people can choose according to their needs and the cost, the budget they have for chip production. And then the system worked properly, 100 megahertz reliably. So we wanted to check if it's reaching the sufficient radiation hardness. And what we do is we irradiate our chips without package. So we bond the chip on the PCB and irradiate it with X-ray. Here you see an X-ray tube. There's a special box because we irradiated small temperature, minus 20 degrees, minus 15 degrees, which we fill with dry air and then irradiate. To reach 1 gigarad, we irradiate with 2 megarads per hour, and then it takes 3 weeks to reach this total dose of 1 gigarad. And as you can see here, some measurements. Here's the output voltage as a function of the total ionizing dose. And it has a very good performance, so we have a variation below 0.2%, even up to 1 gigarad. And our switching frequency is, changing only smaller than 3%. And to the best of our knowledge, this is a world record. So nobody has designed a DC-DC converter with a higher radiation hardness than this. And this was also published in IEEE Transaction on Nuclear Science. Yeah. So another part of the experiment we are involved is the monitoring of pixel system. So this, due to the fact that we have this, let's say, experimental approach with serial powering, where the modules are connected in series instead of in parallel, people fear that we will not be able to switch on the system. So while we have some monitoring capabilities on the pixel, if the pixel chip is not being able to be start up, we cannot use it. Yeah, because if it's integrated on the chip, on the pixel system chip, and the system here, this chain cannot power up, then we will not be able to do some monitoring. And that's why they introduced an additional component in the detector control system, an additional chip, which is monitoring the voltages across the modules and also measuring the temperature. And this was our task, to design this chip. Collect the data via an ADC, send them via a CAN bus to the next station in the detector control system. So here you can see the chip and the block diagram, and the layout is again designed in TSMC 65 nanometer technology because it's so super radiation hard, this technology. We designed an ADC, we designed the bandgap voltage regulator, power and reset, the CAN protocol unit for communication, and then in this experiment, the communication is based on CAN open. CAN open. So while CAN is a automotive bus, so used in the cars, CAN open is a higher level protocol which is used in automation system. It introduces some more structure, how the data is organized. For example, they have these open object dictionaries, so special memory structure, and they have special CAN messages like service data object, process data object, and the experiment project leader said us, please design your chip such that it can talk in CAN open with us. Problem is that CAN open usually is implemented in software. it's not hardware. The CAN protocol unit is hardware. CAN Open is usually implemented in CAN software. And you would need an on-chip microcontroller core to execute the CAN Open software. The problem is that there's no microcontroller around which can operate at this very high radiation and single event rate. And that is why in this chip, we implemented the CAN object on hardware level. So using Verilog, which was really a pain to implement a software in hardware. And the idea came up, why we should not design a microcontroller which can really operate in such an environment. And this is what we did. So what we are doing at the moment, we designed a RISC-V microcontroller core in 65 nanometer technology. It has a 3-stage pipeline. It's operating at 50 megahertz and 1.2 volt. Only thin gate transistors, no thick gate I/O transistors, no 2.5 volt transistors, no 3.3 volt transistors. Everything, even the I/O cells, are designed in 1.2 volt. It has a JTAG interface and it has some peripherals. So how we have to design it so that it is operating in our experiment? We have to introduce error detection and correction. So usually a digital design, a synchronous design is made of, let's say, flip-flops, combinatoric cloud, and flip-flop, right? So what we do, we triplicate everything. We triplicate everything. We triplicate the combinatoric cloud, we triplicate the flip-flops, and then we have a majority voting, which reads the flip-flop reading, and if there's one error of the 3 instances, we correct it, and even we feed this corrected data back into the flip-flop. So in case there's no new data arriving to the flip-flop, the corrected data is fed back so that the errors do not accumulate. This is the way we implemented the whole microprocessor. Every flip-flop, all the logic, everything is triplicated. And then the memory, what we do is we use dual mode memory. And one dual port, sorry, memory. One port is connected to the microcontroller, and the other we do a cyclical error correction. We read the data, we check, and then we write it back. One issue is that we were not, so these macros were from TSMC, we were not sure if the address logic is protected, it's hardened. So that was not written in documentation. We were not sure. So in case an SCU hit the address logic, there is the risk that we write back our corrected data to the wrong address. For example, if we write back an instruction to the wrong address, we corrupt our program and the microcontroller crashes. So that is why because we did not have this information, we even triplicated the memory. Instead of having 1 memory instance, we have 3 memory instances, which gives a huge area overflow, right? Overhead. So here I show you now, we did also TID measurements with X-ray. This I have already shown you. Another type of measurements we do are heavy ion irradiation. So again, we put our chip without package on a PCB, and we put it in such a vacuum chamber where it is then irradiated with heavy ions like xenon, for example. Heavy ions, they are not around in our experiment. They are more in space. But the good thing with heavy ions is that when they've hit the chip, they create a lot of charge, and then it's provocating SUs with very high probability, and you can do good measurement. Right? So this is why this is a good opportunity. So this accelerator facility is in Belgium, close to the NATO headquarters, in Leuven, and close to Brussels. Yeah, what we see is that we measure a specific SU cross section. We can count each SCU, even if it's corrected, we can detect and count it. And we have some special cross-section, and we see that every 8,000 SCU, although we have this amount of protection, we get a crash. And this crash is called single event functional interrupt. We did a lot of investigation because we were not expecting it. At the end, we found that the scrubbing logic, which is cyclically correcting the SRAM, had a TMR protection mistake. So functionally, it's working properly. But if the NSCU hits the scrubber, the corrected data is written back to the wrong address. Thanks a lot. So we had to do redesign. We have made a new design. So the old chip was in 65 nanometer. We have a new version of the chip now in 28 nanometer, which came back from production early this year. And when we return back to Germany, we will power it up and see if it's working. So I have only 5 minutes left, so I have to skip some slides. I'm sorry.
Now, of course, everyone is targeting artificial intelligence machine learning. Yeah? And the question is, how can we design an artificial machine learning hardware accelerator which would be possible to operate in this harsh radiation environment? So everyone who has designed an AI accelerator knows that memory access is dominating power consumption, right? So what is consuming most power is memory access. And if you do the scrubbing, your power consumption even rises. So what we have seen is that the scrubber doubles the power consumption. So in an AI accelerator, power consumption is a problem, and if we do scrubbing, it's an even bigger problem. This is the issue. And the other thing is that the hardware accelerators, they're already quite complex for machine learning, and now if you triplicate it, it will become even more complex. So it's a big issue, and we have to think, and we start thinking about how to implement it to do some kind of maybe predictive maintenance in the experiment, or to do some on detector chip analysis before we read out the data. Yeah? So this could be applications. So, for example, a way to solve it, but we don't know yet, is to analyze the sensitivity of the neural network and to map only the sensitive part of the neural network to protect it to hardened logic. This could be an approach. And what we think there could be a lot of innovation possibly is on the SRAM. We could introduce in-memory computing, so like the people do for artificial intelligence, but we don't do it for artificial intelligence, we do it for error correction. So it's the same operation. You need XORs and all these things. You could do that to apply a Hamming code word-wise on each word of the SRAM asynchronously. And by this means, maybe you save some power because you don't need to read out, correct, and read back. Yeah? This is an idea we have, but we have not started implementing it yet, but we will do in the future. So I was discussing with my PhD students, and they said, Professor, before we can do radiation-hard artificial intelligence, machine learning accelerator, we first have to understand machine learning, and we first have to implement some accelerator without protection, right? This is a correct approach, I agree. So this is what we did the last like 3-4 years. I have very little time left. I will go very quickly through the slides. So what we did, we studied 2 approaches. We designed one accelerator which is application specific, so only one neural network can be implemented and run. And the other approach was we have a multi-purpose, very flexible accelerator which can be configured to run different neural networks. Yeah? So these 2 approaches we studied already. In the first approach, we wanted to see if we can introduce implementation information like area, maximum possible frequency, power consumption into a neural network search algorithm. So we have the TensorFlow or PyTorch or whatever IAML framework. We have a way to map this on hardware. Then we go through the implementation, extract the information like power consumption, clock frequency, area. We combine it with information which comes out of the training and the testing, like inference accuracy, and then we do implement this in a special kind of surrogate model, which is used in network architecture search in AI. And by this means, we run several iterations. At the end, we get an optimized design. This is the idea. We implemented one structure. I don't have time to go into details. Which should be able to run a special time series application, and the design, the RTL design, had some parameters: kernel size, filter numbers in our convolution, and then we run the optimization. And this is the typical output of the optimization. You get several dots, which all of them correspond to one design configuration, and then you have this so-called Pareto front, where all optimal designs are located, and then you can choose according to your needs regarding inference accuracy, the design which gives the smallest power consumption. Okay, so this is one approach we studied, and the other was the more flexible approach. The chip came back from production in January, 28 nanometers. We could power it up, and we could read some internal register, some magic number, which we stored more. I don't know yet. I have to discuss with a PhD student what the results are. So this is a a 2D distributed structure where we have a lot of process elements working in parallel. And we have level 1 and level 2 caches. And all the size of this matrix and the memory sizes we can configure before we synthesize. And then we have the possibility to do a map studying based on the MLIR framework. So if we designed a neural network in our TensorFlow or PyTorch, we have the possibility to study all possible mappings from this network on the hardware and do some optimization and find the one which gives you the highest data throughput at the smallest power consumption. And this then is compiled automatically to a format which is based on instructions which our accelerator can process. So here you see some results. The design reaches an inference accuracy of almost 90%. It consumes like 0.5 square millimeters in 28 nanometer TSMC. It consumes like 10 milliwatt to reach 4.4 teraops. And we can operate like mobile net with 30 frames per second. While this mobile net is quite a huge, although it's already it's for edge computing designed, it's still a relatively a lot of data which has to be put into the accelerator and be processed. Yeah, to conclude, we as IC designers, we are able to contribute to fundamental research, so we can support physicists when studying nature by our expertise. They need our expertise, and it's a good opportunity for engineers to contribute and to go to CERN, to Switzerland, and help the physicists. We have their special challenges like total ionizing dose, single event effects, magnetic field. We need innovative approaches to target this. One approach was serial powering. The other, which we are studying, is high-frequency DC-DC converters with a cascaded power stage and Red Hat microcontrollers. If we introduce artificial intelligence into the detector, we will we get more challenges like increased power consumption in the detector. So we have to think about how to keep the additional power consumption as small as possible. And we will increase circuit complexity and implementation effort, and therefore also new innovative approaches are necessary. Thanks a lot for listening.
Okay, thank you very much, Professor Michael's very excellent talk. Very sorry, because time is limited, maybe only one short question.
Yeah, can I have
okay.
one? A very short question. Yeah. Thank you for the great talk. Yeah. I just have one question about your first slides on the detector part. Yeah. So you use the standard process from TSMC, or is a special process for, I believe that it must be a very long-term project, because you need to develop and then deploy it into the, I would say it's the corridor, right? Yes, yeah. Because we also have a project with Slake, yeah. So I would like, oh yeah. So how much time, from chip to make the subsystem and then deploy it into the corridor? Yeah, thank you.
Very good question. So these projects are always very cost sensitive. So our governments don't want to pay a lot of money for this kind of project, because there's no relation to a real application which you can sell, right? So it should be as low cost as possible. And therefore we use standard technology from TSMC, as low cost as possible, but it proved that TSMC is a very radiation hard process, very good one. We tested several of them, but TSMC was the best. So then the other thing was how much time did it take? So the chip design, 50 collaborators from the US, from Europe, several, from I don't remember which, other, I think from Japan was one group, but I'm not sure. So it took 10 years for chip design only, 10 years for chip design. It was fun to collaborate with this guy, because we had the meetings all around the world. But it took 10 years for chip design, and now it will take like 4 years more to make the modules and to put it right. Yeah, so last year we finished with the chip design process, and now the assembly starts, and it will take 4 more years.
Nice. So I hope that in the near future you can have the opportunity now to receive the Nobel Prize.
The Nobel Prize, the Nobel Prize goes only to the theory. So Peter Higgs, who invented the Higgs, he got the Nobel Prize, but there are like thousands of physicists and engineers required to build this detector.
But they must give you some, the honor or the credit.
It's an honor to be part of this effort, which is sufficient.
Okay, great.
Okay, thank you very much. Thank you, Professor Michael. Excellent.